Alrighty. Find subsequence of length k with largest sum. Easy. Uh, by the way, I didn't do yesterday's deal because it was hard. I looked at it. I thought about it. Thought about some more. Never actually got into anything. So new streak today, and hopefully I can at some point figure out what the hell that last one was about. All right, you're given integer nums, array nums, and integer k. You want to find a subsequence of nums of length k that has the largest sum. This is kind of similar to the last one, like the hard one yesterday. Subsequence length k, or I think the other one was subsequence where k appears sometimes. But anyways, return any subsequence as an integer array of length k. You want to find subsequence of nums as the largest sum. So k. Let's just find a k the largest values, I guess. A subsequence is an array that can be derived from another array by deleting any elements without changing k. So basically find the top two, so it'd be 3, 3. It has to be in that order still, but I guess you can't really leave the order 3, 3. The biggest 3 here would be -1, 3, and 4. And the biggest 2 here would be 3 and 4. Return any, so it could have also been 4, 3. Okay. So I think the simplest thing here what is k going to be? K is going to be up to the length of nums. I think what you would do is I think I'm going to go straight to the optimal solution, or what I consider might be the optimal solution. So if let's say k is 10, then you want to keep track of the 10 largest values. And in that instance, like in theory, you can have like 10 variables and compare variables until you figure out what the lowest variable is. Whenever you see a new value, and see if that value kind of is lower than lowest value, lowest of the 10 values. I have a feeling it should be a heap. It should be a heap that is maintained to be k length, and you're always removing the smallest element of the heap with a new element that's larger than it. So if the heap maintains like the top 10 values that you've seen so far, let's say the array is like 1,000 values, then when you pull something from the heap is something that just has a very fast lookup for what the smallest value is. Well, not even fast lookup, it'll maintain knowledge about what the smallest value in the heap is at all times. With some cost to insertion into the heap, but the insertion is fine. Okay, so here I'm going to maintain heap of size k, compare each new value to smallest value in heap, which is generally the top of the heap. If value is bigger, remove smallest value from heap, and add new value to heap, maintaining k elements in heap. Again, the heap is which is going to be size k, which is basically the top k values in array so far. So heap is going to be declared as that, empty heap. Actually, I should probably start with the first k elements of nums. So nums from the start to k. Start with first k elements. And actually, I think the way that I want to do this is, I want to say heap is heap q. I think it's called heap q, right? It's the variable heap q. So that's the instruction of it. And then for every, let's say n is the number of elements in this array, and then for every index in the range of k to n, the value is equal to nums at this index. This value is smaller than, no, is bigger than the value at the top of the heap, which is the smallest value in the heap. Heap at 0, and I'm going to do heap pop, and then heap push the value. And then at the very end, oh shucks, I can't change the order. Heap doesn't actually keep track of the order. The heap doesn't keep track of the order. The subsequence must be returned in order. I guess the other thing I could do here is I could add to the heap the value, a tuple that is the value and the index, so that I know how to reorder afterwards. It's going to be a little slower than if it was to create tuples. I'm trying to think if I need to. I'm trying to think if I. If there's a better way of doing this. So if I add k elements and I keep track of the smallest element, and maybe the index of the smallest element, I take that index out, then I would need to know what the second smallest is after that. Okay. I'm going to try the tuple. It's going to be a little slower because it needs to instruct that. So I guess I need to actually do something like start with first. So this is going to look a little bad. It's going to be I'll use the list comprehension to instruct this. So it's going to be the value, or let's say value is nums at k, no, nums at I, comma I, for I in the range of k. Okay, so what this does is for every index from 0 to k, so let's say k is 10, so it's like 0 to 9. I'm going to create a tuple that is the nums at that index, nums at 0, nums at 1, nums at 2, comma the index. That's going to be an array form to start the heap with. And then I'm going to compare the value at the top of the heap, which is the smallest value, which is going to be heap at 0, 0, because the value is the first element of the first thing in the tuple. The value is bigger, then I take off that tuple, and then I push onto it the next value, index. Push onto the heap. I wonder if there's a way on heaps to push and pop, or pop and push. There's like a single. Is there a also by hit heap push pop and heap replace for more efficient combining operations? Heap push pop. I don't know this. I wonder if I don't want. I want pop push rather than push pop. So we invoke push add 0 to the list and store the pop element. Push pop method inserts a given item to the heap and pops the smallest. This is push equivalent to push from pop. Push pop. Okay. I think push pop might be a little better for them because it always maintains the same size, or at least a size greater than 1. So it's never null. So I have to check that maybe. Okay, so it's going to be heap pop push. And then at the end, what I would like is I need to convert it back to into an array. So let's say the answer array is 0 times length k for each element in the heap. So while heap is there, I'm going to pop the tuple. So actually I need to sort it. No? I need to sort the heap based on the based on the index of each tuple. Shucks. How do I do that? Sort it based on the index of the tuple. So I think I do something like heap dot sort key is, oh gosh, what is the syntax? Key equals lambda x, where x uses the first element of it. Oh gosh, key sort list. Let's see, lambda key equals lambda x, where x is the square. I think that's correct. So I'm sorting based on the index of the tuple, which is the second element inside the tuple, and then I go answer equals k value for every well, the values can be nums at 0, nums at it's going to be nums at I at 0 for every I in range of k. No, it's not nums at I, it's going to be heap at I. That's 0 for I in range k. I don't know if this works. Q. Object module is not callable. Why is this not callable? It's constructor for heap Q. I guess I need to use a heapify instead. I thought I could just start with. I could start with a. Okay. Heapify heap Q. Does heapify actually return the list? No, it doesn't. Okay. Heap is equal to, I guess, this stuff. Well, heap is equal to this stuff. The initial list, and then heap q dot heapify. Is that the syntax? Yeah. Okay. Heap push, heap pop push. Oops. Heap push pop. See how this runs in the bigger test case. Whoa, back to a streak. Huh. Okay. So this is fine. So I create my heap, or I create my list of tuples that has my first k tuples. I make that into a heap, so it basically orders it so that it knows where the minimum is. Then it goes through later values, compares the values to the smallest value in the heap. If it's bigger, then that means it's one of the top k values. Then it pushes the tuple of that value and where it is. Afterwards, I sort the heap based on the index value. So for every tuple, the key of the sort is going to be the first the index within the tuple, which is the element the tuple at index 1. Tuple at index 0 is the value, tuple index 1 is the index, so it's the key of how I want to sort the list basically. And then I convert the list of tuples back into a list of just values, where the values is the first element of the tuple, index 0. Now I'm trying to think of whether or not this is if there's a better way of doing this. So the other way I can do this is I can maybe more simply create a whole, I can sort the array based on size, keeping also information about the index. Okay, I'm just going to try the alternative approach here. So how big is this thing? 1,000? That's pretty fast. Okay, so tuples is going to be nums at I, comma I in the range of n, where n is the length of nums, and then I'm going to sort the tuples. This is going to sort by the first element of the tuple, which is going to be the value. And then I'm going to pull out the I'm going to pull out the first k elements and resort that. So top k is going to be actually it's going to this is going to sort in the wrong order. It's going to be sorting small to largest. So I think I need to make the tuples be negative to make it sort, to make the values negative. The values initially can be negative. That's fine. So anyways, make values negative so that when I sort it, it goes in kind of descending order, which is biggest to smallest, but the biggest is like kind of negative version of it. So then top k is going to be the top tuples. So it's going to be not I, nums at not tuples at I for I in the range of k. So the top k tuples, and then I'll sort that again based on the index. So key is lambda x, where I'm using the first element of the tuple, or the second element tuple, the next one element, which is the index, and then answer is equal to every value in the sorted top. So it's the top k at I 0 for I in the range of k. Oh, oops. This is also supposed to be the negative of that. Since this is currently negative. Missing syntax for I in range. Okay. In range n. Wow. I and n is just too close to my mind, so it's just missing words. Alright, see how fast this one goes. I think in theory this is going to be slower because what you're doing here is you're sorting the whole array at this point right here. So so if the array is, let's say, 1,000, right, then you're sorting 1,000 log 1,000 to do that. N log n is the sorting speed, efficient sorting speed. And even though you are sorting here you're sorting based on the heap size, or you're sorting something that is the size of the heap, which is the top k elements. So this is sorting k log k rather than n log n, even though in theory n is also proportional to the size of k. In practice, n is going to be probably like larger, and k is going to be smaller, so therefore this is basically going to be faster. Yeah, well, yeah, you're maintaining sorts that are k long. So each time you insert here, it's going to be log k to insert, or to maintain the heap. I'm pretty sure, because I don't think the heap is sorted. I think it's just maintained. Yeah, the heap, when you insert, it's log k, where k is the size of the heap. And then you're doing that n times, so because each loop goes through one index of the array. So it's like n log k is this whole cost here. There's another k log k to do the heap sort here, and then some conversion stuff. Yeah. Okay. This is the other way. Although, because the sizes were so small, I didn't know if it was actually all that much more speed-wise on the results, the accepted results. Okay, so summary. This is going to be, well, man, is this really considered easy? I guess this is easy in the sense that there were other maybe non-efficient ways of doing this that could have gotten there, but I don't think heaps were generally something I learned in the simpler portions of it. Anyways, summary. This is going to maintain a heap of size k for the top k elements, k values in array. Whenever a new value is considered, compare to smallest of k values in heap, which is the heap at 0, basically, assuming you're not dealing with tuples, but anyways. And replace, by which I mean replace if new value is bigger, which is pop and push new value. Secondarily, actually, just additionally, since the order of the elements matter, here we're returning a subsequence rather than just top k values in array. I kept track of the indices of the values by having heap of tuples value comma index instead of just values, and that boiled down to when I first create the heap, I'm creating it based on a tuple nums at index, which is the value and the index itself, and then when I compare the value to the top tuples value, so top tuple in the heap, and then or lowest tuple in the heap, and then value of that tuple, which is the element index 0 of the tuple. And then when you push the value in index. And lastly, and then at the end, after iterating over all elements, convert, sort heap of tuples based on index, and that's using most directly just using key function of the sort in Python, and convert the index sorted heap to array of just values. And that's using this line of list comprehension for every index in range of k, which is the size of the heap, and get the value of the tuple at that index in the heap. Time complexity is going to be O of, this is interesting, this is going to be O of n log k, since the main for loop, iterates over n elements, n values, and does a and possibly does a push, a pop push. Pop is constant speed, but push possibly does a push of a new value into heap. And to maintain heap, kind of, what's the word that I'm looking for? Heap's intrinsic property. Heap intrinsic property. There's a word for that. Like there's something about that describes some facet of like a particular property or trait of a structure. The heap's intrinsic property whereby it's always able to get the minimum at, or keep the minimum at the very top. And to maintain a heap intrinsic property during insertion is O of log x, where x is size of heap. So anyways, because the heap is size k, then we log k to do that, and then you're iterating over n elements, so n times log k. And then sorting heap afterwards based on index is O of k log k, as k is size of that array, and converting to array to the answer array of values is O of k. So overall, this is going to be O of n log k, since that's the biggest factor and all that. You do O of n log k plus O of k log k plus O of k. This thing's going to be dominating. Space complexity is going to be O of OK to maintain, to have a heap of size k. And I mean, in theory, you could maybe have the answer array, which needs to have size k anyways. You can, in theory, could use space of answer array, which is size k, as heap during calculations, in which case no extra kind of space is needed, and space complexity is there for O of 1. But since I didn't do that optimization, this heap was definitely extra memory than this answer array. So, okay, cool beans.